Right now, sitting in a NASA image archive, there is a nighttime satellite photograph that looks almost too perfect to be real. A series of faint, glowing rings, nearly complete circles, ripple outward from a single point over the North Pacific Ocean, stacked one inside the other like the pattern a stone makes when it is dropped into still water. Except this was not water. It was the mesosphere, a layer of atmosphere roughly 50 miles above the surface of the Earth, close enough to the boundary of space that satellites orbit above it rather than through it. And the stone that caused it was not a stone at all. It was Super Typhoon Sinlaku, a storm that exploded from a Category 2 into a Category 5 equivalent typhoon in about 24 hours this past April. And scientists studying the satellite data afterward found that its violence had not stopped at the ocean's surface. It had reached all the way up into the edge of space itself in a pattern so clean and so complete that the researchers who found it were genuinely surprised by what they were looking at. This is the story of what scientists just discovered inside one of this year's most powerful storms, why almost nobody expected to see it this clearly, and what it might mean for how we track dangerous storms in the future. No hype, no exaggeration, just what the data from NASA, NOAA, and the researchers who studied it are actually saying. If you remember hearing about Sinlaku when it tracked near Guam earlier this year, drop a comment and tell me what you remember about it. I read every one of these. If you want grounded storm coverage instead of panic headlines, subscribe. It is free, and A-like helps this reach people who find this stuff as fascinating as I do. Let us go for 5,000 likes on this one. Thank you. Now let us get into it. First, a quick but important clarification, because it is easy to mix these two things up, and they are not remotely the same phenomenon. What Sinlaku produced are called atmospheric gravity waves, not gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, produced by colliding black holes and detected by giant laser instruments built specifically to catch them. Atmospheric gravity waves are something far more down to earth in every sense of the phrase. They are oscillations in ordinary air, produced whenever a parcel of air gets forcefully pushed up or down and gravity pulls it back toward its original position, causing it to overshoot, swing back, and settle into a rippling wave-like pattern. The same basic physics behind ripples spreading across a pond after a stone breaks the surface. The two phenomena share a name by coincidence of physics vocabulary and nothing else. To understand why Sinlaku produced them so dramatically, you need to picture what was happening at the very center of the storm as it intensified. Tropical cyclones are powered by latent heat, the energy released when water vapor condenses into liquid water inside towering thunderstorm clouds. In an ordinary storm, that heat release drives strong but relatively contained convection. In a storm undergoing the kind of explosive strengthening Sinlaku went through, jumping from Category 2 to Category 5, equivalent intensity in a single day, that heat release becomes so intense that individual thunderstorm towers near the eyewall punch straight through the top of the troposphere, overshooting into the stratosphere above like a fist through a ceiling. Each one of those overshooting towers slams into stable air above it, and that collision forces the surrounding air to oscillate, generating a gravity wave that then propagates outward and upward, layer by layer, growing larger and more spread out as it moves into thinner and thinner air, exactly the way ripples on a pond spread outward and grow fainter the farther they travel from where the stone landed. Unlike ripples on a pond, though, these waves did not stay near the storm that created them. Satellite observations showed them traveling thousands of miles outward from Sinlaku's center, expanding and evolving as they move through successive layers of the atmosphere, a scale that is difficult to appreciate from the ground, where the tallest storm clouds most of us will ever see rise only a handful of miles into the sky rather than the tens of miles these waves ultimately covered. What made Sinlaku's version of this so remarkable is not that the waves existed. Researchers have understood in theory for years that tropical cyclones can generate gravity waves this way, and earlier modeling work had already predicted that spiral-shaped gravity waves should radiate outward from an intensifying storm's eyewall. What surprised the scientists studying Sinlaku was how intact and how completely visible the pattern remained by the time it reached the mesosphere, 50 miles up. Normally, winds at those altitudes shear apart and scatter a gravity wave long before it can form anything resembling a clean, concentric ring. In Sinlaku's case, the stratospheric winds at the storm's particular latitude happened to be unusually weak in April of this year, which meant the waves were not torn apart on their way up, and instead arrived at the mesosphere still largely intact. One of the atmospheric scientists who reviewed the imagery said she was genuinely surprised to see nearly complete rings in the glow above the storm, a level of clarity researchers do not get to observe very often. The way scientists actually saw this is its own small piece of remarkable timing. The rings became visible through a phenomenon called airglow, a faint natural light produced when atoms and molecules in the upper atmosphere release energy they had absorbed from sunlight earlier in the day, essentially the sky glowing very dimly, all on its own after dark. That glow is ordinarily too faint to see clearly, especially with any significant moonlight washing it out. On the night the imagery was captured, the 12th of April, the moon was only about 25% illuminated, dark enough that the FIRES instrument aboard the NOAA-20 satellite, which is capable of detecting extremely low levels of nighttime light, could pick up the air glow clearly enough to reveal the full ring pattern rippling outward from the storm below. A single night with slightly more moonlight, or slightly stronger, stratospheric winds at that specific latitude, and this exact image most likely never gets captured at all. Separately, NASA's Aqua satellite, using an instrument called the Atmospheric Infrared Sounder, independently detected the thermal signature of the same gravity waves lower down in the stratosphere, confirming that the disturbance was a real, physically continuous structure extending from the storm's eye wall all the way up through multiple layers of atmosphere, rather than an isolated visual coincidence at one single altitude. This is where the discovery stops being simply beautiful and starts being genuinely useful, and it connects directly to one of the hardest ongoing problems in storm forecasting. The gravity waves Sinlaku produced were not a random side effect, unrelated to its intensity. They appeared specifically during the 24-hour window when the storm was rocketing from Category 2 to Category 5 equivalent strength, meaning the waves themselves are a visible, remotely detectable signature of a storm undergoing rapid intensification. The exact phenomenon that made Hurricane Otis catch forecasters so badly off guard when it exploded from a weak tropical storm to a Category 5 hurricane off the coast of Mexico in 2023. One researcher studying the connection explained the practical goal plainly, saying scientists specifically to help determine whether a storm is intensifying, since that kind of rapid strengthening is notoriously difficult to track. Reliably over open ocean, far from any coastline, where reconnaissance aircraft cannot always reach a storm in time to sample its inner core directly. A storm's gravity wave signature, by contrast, can in principle be observed continuously from a geostationary satellite that never has to leave its fixed position above the ocean, watching the same patch of sky non-stop rather than needing a flight crew to physically fly into danger to gather the same information. That distinction matters enormously in practice, since the storms that pose the greatest forecasting challenge are consistently the ones sitting hundreds of miles from the nearest coastline or reconnaissance base, exactly the kind of blind spot that turned Otis into a nightmare scenario with only a few hours of real warning, rather than the day or two that a more predictable storm typically allows. There is an even stranger thread running through this discovery, one that stretches the implications of a single typhoon well beyond ordinary weather forecasting entirely. Gravity waves that reach high enough into the atmosphere do not necessarily stop at the mesosphere. Researchers studying the connection between tropical cyclones and the ionosphere, the electrically charged layer of atmosphere that sits above the mesosphere and plays a direct role in how GPS signals and long-range radio communications travel around the planet, have previously observed signatures of hurricanes showing up in ionospheric weather. Gravity waves strong enough to reach that high can trigger what are called traveling ionospheric disturbances, along with structures known as plasma bubbles, both of which are capable of interfering with GPS accuracy and radio communication signals passing through that layer of atmosphere. One researcher working on this connection put it directly, saying that in the world of space weather specifically, a single event like a tropical cyclone can turn out to be genuinely significant, precisely because most people, understandably, never think to connect a typhoon churning over the Pacific Ocean to a GPS signal briefly wobbling in accuracy thousands of miles away or hundreds of miles straight up. This particular corner of research sits at the intersection of two scientific communities that do not always talk to each other very much. Meteorologists who study storms at the surface and space weather, physicists who study the ionosphere and its effects on modern satellite-based technology. And a discovery like Sinlaku's near-perfect gravity wave rings gives both groups a genuinely useful, unusually clean case study to work from together. It is worth being honest and precise about what part of this story is the actual discovery, since it is easy to overstate. Scientists were not surprised that a violently intensifying typhoon could theoretically generate gravity waves reaching the upper atmosphere. That basic physical relationship had already been described in prior research, modeling how tropical cyclones radiate this kind of spiral wave pattern outward from their eye walls. What genuinely surprised the researchers here was the sheer completeness and clarity of what they observed, a rare, nearly perfect set of concentric rings visible all the way up to the edge of space, made possible by an unusual and temporary combination of weak stratospheric winds and a dark enough night sky to actually see it. It is the observational confirmation, this specific, unusually clean example, that scientists are treating as the genuinely new and valuable part of the story, not the underlying theory itself, which had existed in the scientific literature for years. without anyone having captured quite this clear an example of it actually happening. Sinlaku itself is worth remembering in its own right, since the storm behind this discovery was already a significant weather event on its own before anyone noticed what it was doing to the upper atmosphere. It tracked just southeast of Guam in mid-April, reaching winds reported around 185 miles per hour at its peak, making it the strongest tropical cyclone recorded anywhere on the planet up to that point in the year. It brought heavy rain and flooding to the Mariana Islands, killed 17 people, and caused roughly $1.5 billion in damage across Guam and the northern Mariana Islands. Meteorologists at the time noted that a tropical cyclone of that intensity occurring that early in the Pacific season was itself genuinely unusual, a distinction Sinlaku held before anyone had even examined what its gravity waves were doing, 50 miles above the ocean it was tearing across. The storm was later formally classified by the Japan Meteorological Agency as a violent typhoon, the highest intensity category on the scale that agency uses, a designation roughly equivalent to a Category 5 hurricane and one reserved for only the most extreme tropical cyclones the North Pacific produces in a given year, coming only months after a separate Category 5 storm had already formed over the remote southern Indian Ocean earlier that same year. Sinlaku's rapid strengthening added to what was already shaping up as an unusually active year for the most extreme tier of tropical cyclone intensity worldwide, well before anyone had connected any of it to what was happening in the mesosphere above. So what does all of this actually mean for you, watching this wherever a hurricane or typhoon eventually threatens your coastline? It does not mean satellites are already using gravity wave detection to issue storm warnings today, and it would be dishonest to suggest this discovery is an immediately deployable early warning system. Researchers are still working through the basic science of how consistently these wave signatures appear across different storms, before anything resembling an operational forecasting tool could realistically be built on top of it. What it does mean is that researchers now have a genuinely promising new avenue to explore for one of forecasting's most persistent blind spots, catching the earliest signs of rapid intensification in storms sitting far from any coastline, long before an aircraft can physically reach them to confirm what is happening inside. It also means something broader and honestly a little humbling about how connected the different layers of this planet's atmosphere actually are. A storm violent enough to flood an island chain and kill 17 people at the ocean's surface was, at the exact same time, quietly rippling the edge of space itself, in a way that could theoretically nudge a GPS signal used by someone thousands of miles away who has never heard of Sinlaku and never will. The next time a hurricane or typhoon forecast crosses your feed, it is worth remembering that the storm itself is really only the part of the story happening down at sea level, and that an entire second, largely invisible version of the same event may be unfolding 50 miles straight up at the very same moment. The honest, grounded summary of this discovery is this. In April of this year, Super Typhoon Sinlaku intensified from a Category 2 storm into a Category 5 equivalent typhoon in about 24 hours, and during that exact window, satellites captured it, generating atmospheric gravity waves so intact and so clearly visible, rippling outward through the stratosphere and into the mesosphere nearly 50 miles up, that the scientists reviewing the imagery described being genuinely surprised by how complete the pattern was. The waves formed because towering thunderstorm clouds near the eye wall punched through the troposphere and disturbed the stable air above them, and they survived their journey upward largely intact because of an unusual combination of weak stratospheric winds and a dark enough camera. Because these waves appeared specifically during the storm's most explosive strengthening, researchers now see a genuine, if still early, opportunity to use this kind of remote signature as an additional tool for spotting rapid intensification in storms far out at sea, the same blind spot behind forecasting failures like Hurricane Otis. And because gravity waves strong enough to reach the upper atmosphere can ripple further still into the ionosphere itself, a single typhoon over the Pacific carries the theoretical potential to nudge GPS and radio signals used across an entirely different part of the planet, a genuinely strange reminder that the atmosphere above your head and the one at the edge of space are not two separate systems at all. We are going to keep an eye out for the next storm that produces something like this, sourced the same way we did today, straight from NASA's Earth Observatory, NOAA, and the researchers actually studying how tropical cyclones connect to the upper atmosphere, not recycled headlines dressed up as breaking news. Subscribe so you do not miss it the next time a storm does something nobody expected, because storms like Sinlaku suggest it is only a matter of time before another one does, particularly with an unusually active year for extreme tropical cyclones, already producing multiple Category 5 equivalent storms well before the season's traditional peak. And leave that comment below. Tell me if you had ever heard that a hurricane or typhoon could physically reach the edge of space before today. because behind every one of these satellite images is a family in the Mariana Islands who lived through Sinlaku's flooding at ground. Level with no idea that the same storm was rippling the sky 50 miles above their heads, and a researcher somewhere who spent a quiet April night staring at a nearly perfect set of rings on a screen, genuinely surprised by what the ocean below had just done. 5,000 likes on this one. Let us go. See you in the next one.